Okay, in this problem, we're looking at the heights of a simple random sample of 400 students. The sample mean is 66.2. Suppose the heights follow a normal distribution, which is important because then we know our conditions would be met. And we have a standard deviation of 4.1. Notice this is the population standard deviation, so we're going to want to use a z confidence interval. So I always write down my information. I have n equals 400. X bar equals 66.2, sigma equals 4.1, and is normal. Okay, to use a z confidence interval, you have to have a large sample size of at least 30, which we have, or a normal distribution, which we also have. Okay, a z confidence interval, the formula is x bar plus or minus z star, sigma over square root of n. So let's come over here to find z star. If I was to draw a picture, I want a 95% confidence interval. So that means 0.95 in the middle, which means 0.025 in each tail. So I'm going to pull up my standard normal table. And I'm going to look for 0.025 in that left area. So I'm looking for an area of 0.025. So 0.025, here it is. So I'm at z equals negative 1.96. So that had an area of 0.025 to the left, so this is negative 1.96, which means by symmetry this will be positive 1.96. Or if you want, you could have looked up from here all the way over, it would be 0.975, and you could have looked up that area to get positive 1.96. But that is my z star. So we just plug it all in, so 66.2 plus or minus z star, which is 1.96, times sigma, which is 4.1, over the square root of 400. And I got 65.8 to 66.6, so that's C for us. So we'd be 95% confident that our true population mean height, so the average for all of the male high school sophomores would be in between 65.8 and 66.6 inches. Now B says, suppose the heights of a simple random sample of 100 sophomores was measured rather than 400. And we want to know what happened to our margin of error. So to do this, you could just stick in 100 right there. So what would happen if we put a 100 in instead of 400? So you could do this, and you would realize that we're dividing by a smaller number, which means our overall result will be bigger. Okay. So in our case, smaller n means bigger margin of error. Okay. If you want, you could go back to your old learning packets. This is in Confidence Intervals Part 1, and it talks all about the margin of error. We have a whole section on the margin of error. But a smaller sample size means a bigger margin of error. Usually we think about it the other way. We say, oh, a bigger sample size means we'd be smaller margin of error. So we just kind of reverse that here. So the margin of error would increase, so A. And then we also had a question on 21. Suppose we wish to calculate a 90% confidence interval for the average amount spent on books by freshmen. The interval is to have a margin of error of 2. Assume that the amount spent has a normal distribution, so that means we can use our formulas, with a standard deviation of 30. How many observations are required to achieve this margin of error? I just barely realized that this part got cut out of your notes this year. Okay. So to find how many observations you need for a certain margin of error, I didn't put that formula in, but you can still certainly do it. Because we know that our margin of error, let's call that M for margin of error, is equal to z star times sigma over square root of n. Basically, your margin of error is just the part that you're adding or subtracting here. So that's what we're adding or subtracting. Okay, so you plug in everything that we know. So we want a margin of error to be 2. So we're going to have 2 equals z star. So we need a 90% z star. So this would be 0.90 in the middle, so 0.05 in each tail. If I look up this 0.05 here on my normal table, I'm looking for 0.05 in the middle. Looks like I'm in between negative 1.64 and negative 1.65, so let's kind of go in the middle, so negative 1.645. So this is negative 1.645, which means this would be 1.645. So z star equals 1.645. So let's see, we want our margin of error of 2 is equal to z star of 1.645 times sigma, which is 30, divided by the square root of n. N is the only thing we don't know. So now we just solve for n. And to do this, you just pretend you're back in an algebra course again, and let's multiply both sides by the square root of n. So 2 square roots of n equal, and let's put 1.645 times 30 in our calculator. So 49.35. Let's divide both sides by 2, so square root of n equals 24.675, and square both sides to get 608.8, and we always round up, so 609. So we round up because a bigger sample size is always better, so that's why we round up for sample size.